Hello and welcome back. This is a BitLearn series on modern operating system design. So this series is not about using an operating system. This series is a little more academic for people who want to understand how an operating system is designed, how it works. It is about focusing on the ideas, the abstractions, the trade-offs, drawing primarily from academic foundations. The goal is simple: to understand why operating systems look the way they do today. If you use computers for work or building systems, this series is meant to give you the mental models behind how it is designed. So let's dive into it. So this one will be episode 0, or the preamble for the entire mini series on operating system design. So I'll try to keep it as short as possible, just enough context, just enough history to understand why operating systems look the way they do today. Okay, so with that, let's get started. What is an operating system really? Before we talk about processes, memory, files, or security, we need to answer a very simple question. Why does an operating system exist at all? Why do we need it? So you use Windows, you use Linux, you use all sorts of operating systems, but why? So modern computers, they feel effortless, right? You open multiple programs, you open a music player, you probably open a browser, and you save something. The files will exist across the restarts. Even when you turn off the machine, your data stays. So even if one application crashes, it rarely brings down the entire machine. So this sense of stability, it feels very natural when you start up your computer. But it is not. Everything we take for granted in computing today is actually very carefully constructed. And at the center of all that construction sits the operating system. So let's talk about what was the world like before operating systems. In the earliest days of computing, there were no operating systems. Not in the modern sense. A computer ran one program at a time. A single user loaded a program, the program executed, and when it finished, the machine stopped. You could imagine days when you had huge mainframes or these large computers in clean rooms, and people used to load their program on punch cards or tapes or all sorts of input mechanisms. There was no multitasking. The whole computer was dedicated for just that one program. There was no file system. It doesn't remember anything. Whatever you want to remember is out on a punch card. You have to hold all your punch cards in the right order so that you remember what the computer told you. There was no protection between programs. The computer was essentially an extension of the program itself. So the hardware is essentially an extension of the program. You have written a program to, let's say, compute pi for up to 6 decimal places. When you run that program, the computer is fully dedicated for you. All the vacuum tubes, all the circuits, that whole clean room, everything is just you. So the computer is essentially an extension of the program itself. So that's why I would like to say there was no operating system. This model worked when computers were rare and isolated, and they were very useful when you had narrowly defined tasks. But it broke down very quickly as computers became more powerful and more people started to use the computer. So the first problem was wasted hardware. So between the time spent when one user loads his program, takes his output, then another user comes in, he loads his program, there is wasted hardware. It's very expensive in those days to have a huge room full of hardware, and it's just lying there. Early computers were expensive machines that spent most of their time idle. Setting up programs took longer than running them, so human operators waited while machines did nothing. So the earliest operating systems emerged to solve a very practical problem: how to keep the hardware busy, get the most out of it. I don't want the whole hardware to be just waiting, using electricity, while another user comes in with his tapes or whatever mechanism he has for his programs. So these systems was very simple. They queued the job, they loaded programs automatically and executed them one after another. This was probably the earliest modern operating systems, where you can queue jobs, have all the users come and queue all their jobs, and the computer will run them one after the other. So it is still dedicated for one program at a time. There was very little elegance in their design, but efficiency was the only goal. You want to efficiently use the hardware. So from the beginning, this established a very crucial truth. An operating system does not exist to serve programs. It exists to manage hardware. So that is how it began. So that is one of the ways, or one of the definitions of how operating systems started evolving. It existed to manage hardware because hardware is expensive. But from hardware management, we go into conflict management. So, as computers became shared resources, new challenges appeared. Multiple users, they're trying to run all their programs. Programs interfered with each other. A single faulty program could crash the whole system. So, it started going into areas that modern operating systems solve today. It had to balance how to manage fair access between programs, how to isolate users, how performance is more important, where can I do a trade-off between safety. So this shift from machine-centric computing to human-centric computing, this kind of marks the birth of the modern operating system. There is no single day or a single date, but it's a mindset that starts changing. Now let's look at the three fundamental illusions. At the heart of every modern operating system lies a set of carefully maintained illusions. So what are these illusions? These illusions are not side effects. They are the primary service an OS provides. So first one is the illusion of a private CPU. You feel like you have the entire CPU for yourself. Today when you run your browser, it feels like the browser has the whole computer for itself. It's an illusion. Each running program behaves as if it owns the processor. In reality, the CPU is shared among many programs. So the operating system creates this illusion through a lot of different concepts like scheduling, context switching, time slicing. We will look into all of those things in this series. Programs are not running in parallel. They are being rotated very rapidly, often millions of times per second. I know it sounds crazy, but that's how it works. What the program perceives as continuous execution is in fact controlled interruption. So we'll look at interrupts, we'll look at the mechanisms as we go into the series. So that was the first illusion, the illusion of a private CPU. It's not private, but it feels like it. Then you have this illusion of infinite memory. If I have a web browser which is loading a huge website with, thousands and thousands of pages on that, if your computer has enough memory, it feels like you have all the entire memory dedicated for you. So programs act as if they have access to large contiguous blocks of memory. In reality, it is limited, fragmented, and it is shared across multiple programs. So the operating system kind of hides this complexity through virtual memory, address spaces, paging, all of these topics. So that is the second illusion, the illusion of infinite memory. Then we have the illusion of safe isolation. You know that you're running a browser, you're visiting some crazy site, but if the browser fails, you know that it doesn't affect the rest of the computer. Your YouTube still runs, your music player is still running, only the browser crashed. As long as they are in different browsers. So the illusion of safe isolation, it assumes that the other programs cannot corrupt them and the system will survive their failure. So this illusion is enforced through ideas like hardware support, protection mechanism, separation between user mode, kernel mode. So without it, modern multi-user, multi-application systems would be impossible. So it's not wrong to summarize this entire operating system as an illusionist. These three illusions reveal a very powerful way to think about operating systems. An operating system is an illusionist. It is positioned between the software and hardware. It lies, but carefully, consistently, and safely. When I say lies, it is lying. It's giving you false information. Is it? Or is it giving you a false sense of safety? So these are lies that are designed by design. They are not really faking anything. They are trying to give you a standardized interface to a lot of things. So why does this structure matter? So if you look at how an operating system itself should be organized, should it be one large program, or should it be a collection of smaller services, or is it like a minimal core with supporting components? There are many ways to design an operating system. So different answers to these questions gave rise to entirely different families of operating systems. So these design philosophies are explored in modern textbooks. One of them I can suggest is the Modern Operating Systems by Andrew S. Tanenbaum, one of my favorites. So go try it out. It treats operating systems not as a collection of features, but as carefully reasoned engineering systems. So this episode or this mini series will also follow the same tradition. It's not about commands, system calls, or kernel hacking. We will look at why operating systems are designed the way they are, the trade-offs behind these core abstractions, and how modern systems evolved from first principles. So understanding these foundations kind of makes higher level systems, databases, distributed systems, cloud platforms and all the other modern things much easier to reason about and understand. So looking ahead, an operating system is not just software, it is a philosophy about how limited resources should be shared. So in the next episodes, we will explore the first major design decision every operating system must make. How should it be structured? So till then, thank you for watching. Do subscribe, do like, and I hope you enjoy learning operating system design along with me. Thank you.